Welcome to the course on biostatistics and design of experiments. We completed what we want to talk about in screening designs, and we started on the second order designs. Second order designs are generally done after you screen all the unwanted factors and come down to a limited number of factors. Second order designs are quadratic in nature, so we can develop regression models which has second order terms, which has square terms and so on. Actually, the first one we looked at is called the central composite design. So, in the central composite design, I mentioned, suppose you take a 2 power 3 type of design, that means 3 factors, 2 levels, 2 raised to the power 3 design. So, what you have? You have a cube, 2 raised to the power is 3 is 8 experiments, 2 into 2 into 2. So, this could be factor 1, this could be factor 2, this could be factor 3. So, we have 8 experiments. Then we add one extra experiment in the center, then we also add 6 experiments away from the face of the cube. Okay. This is the face of the cube, so away from it. So, you have 6 phases for a cube. So, you have 6 experiments. So, this adds up to 8 plus 1 9 plus 6, that gives you 15 experiments, and by doing 15 experiments you are changing each of the factor 5 levels. This is better than a 3 power 3 type of design, a full factorial design with 3 levels and 3 factors, that will be 3 into 3 into 3 is 27, whereas with 15 experiments I am able to change each of the factor 5 levels, whereas a 3 power 3 design will change each of the factor only 3 levels. Okay. So, that way this is extremely powerful. Then we have this box Benham design. This is also similar to that, only thing is instead of the corner points, it takes the points at the edges of the cube, okay, at the edges of the cube. Okay. That is the only difference. Okay. So, it does not have the corners, it takes the edges of the cube. So, let us go back. So, suppose if we have a 2 by 2 system, that is 2 raised to the power 2, 2 factors only, you have 4 experiments at the corners, that is the factorial points, then 1 experiment in the center, and then you pick up 4 experiments outside this square. Okay. This we call it alpha, alpha greater than 1. If alpha is equal to 1, it will be lying exactly at the edges. Okay. Okay, then that is like your plus 1, 0, minus 1 type of experiment. Okay. Whereas in the alpha case, what we are doing is we are having plus 1, 0, minus 1, in addition we have plus alpha and minus alpha for each of the parameters. Do you understand? Now, the question is, how do I decide on the alpha? So, it has been found that alpha square root of the number of parameters is most optimum. That means, if it is a 2 raised to the power 2, then alpha should be 1.414. So, if your square has a side of 1, then alpha should be 1.414. Okay. That will be a point. So, the experiments here is plus 1, 0, minus 1, plus 1.414, minus 1.414 for each of the parameter, that is how it will, or alpha you call it. So, as I said, generally it has been found square root of a number of parameters gives you the best optimum results. So, if it is a 3 parameter problem, we will do square root of 3, if it is a, that is 1.732, if it is a 6 dimension square root of 6, that is 2.44. So, this is a good number to have for alpha. Okay. So, if you compare it with your 3k factorial design, okay, so for a 2 factor 3 level, 3 raised to the power 2, 3 into 3 is 9, CCD also will give you 9, that is for 2 factorial. Okay. 1 2 3 4 5 6 7 8 9, right. So, the number of experiments is the same, but like last time I told you, if I am doing a factorial 2 raised to the power 3, I am looking at each factor only at 3 levels, right. Whereas, when I use a CCD, I am looking at each factor at 5 levels. So, I will get better nonlinear relationship. Now, let us go to 3 factor problem, that 3 levels, 3 power 3, 3 power 3 is 3 into 3 into 3, that will come out to be 27 experiments, whereas with CCD, okay, with CCD I can do 15 experiments. This is the 2 power 3 8 experiment, then center, and then 6 star points, 15 experiments. You see I am reduced experiments dramatically. Now go to 4, 3 raised to the power 4, 81 experiments. CCD I just do 25 experiments. 5 factors, 3 raised to the power 4, 243 experiments, whereas I get 43 experiments in CCD. So number of experiments goes down dramatically. It has got lower variance because I am looking at different levels of each of these factors. Of course I can go to fractional factorial of this, we will look at a number of experiments also as we go along, and we do a fractional factorial of 3k. The Box-Benken design for 3 factors is given like this. So it is at 3 levels. So we have minus 0 and plus. So as you can see here we have minus, minus 0, minus plus 0 and so on. So there are 15 experiments in this particular set. Okay. Basically what you are doing is you are doing experiments at these places, these 4 corners, plus you have a central run. Okay, we are doing 3 central runs, and then we are also doing experiments at these phases. So there will be 6 phases actually. Okay, so 8 corners, 6 phases, okay, and then we have doing at the center. It can be represented in this short form, A as plus or minus, B as plus or minus, and C in 0. That will make up 4 experiments, because A at plus, and then A at minus, B at plus, and B at minus. Then we do A plus or minus, C plus or minus, and B will be in 0. That means A plus or minus, C plus or minus. So that is again 4 experiments. Then A will be in 0 and B and C plus or minus, that will be 4 experiments, and 3 experiments at the central point. So they all add up to 15. This is called the shorthand notation, and this is the normal for which we are used to. Okay, so when we talk about say plus or minus, plus or minus, plus or minus for A and B and C as 0, this is exactly this. The first 4 experiments are A going both plus or minus, B going both plus or minus, and C going 0, and the 5th experiment is 0 0 0, that is the central point. So we have 3 places where we have the experiments done at the central point. So this adds up to 15 experiments. So suppose we have 4 factors, the Box-Benken design, 4 factors, namely A, B, C, D. Again the same approach, we have A plus or minus, B plus or minus, C and D are maintained at 0. So that adds up to 4 experiments. Then we have A and B at 0, C and D on plus or minus, that adds up to 4 experiments, and then this is at the center point. So that comes to 1 experiment, and then we do A and D at plus or minus, B and C at 0, that is 4 experiments, and then B and C at plus or minus, and A and D are maintained at 0, that is 4 experiments, and then 1 central point, and then we do A at plus or minus, C at plus or minus, that comes to 4 experiments, then B at plus or minus, D at plus or minus, that comes to 4 experiments, and again another center point, that is 1 experiment. So they all add up to 27. So this is called the shorthand notation, and this is the longhand notation. This is the normal, we are used to it, and so when you are doing a Box-Benken design for 4 factors, we have to do 27 experiments. So when we are doing a Box-Benken design for 3 factors, we do 15 experiments. So if you are doing 5 parameters, that means A or 5 factors, A, B, C, D, E, okay, then we can develop in the same way. The shorthand notation is given, and you end up with 46 experiments. Okay. So we have A, B plus or minus, C, D, E are maintained at 0, like that you keep on varying, and then you also have these center points. So you do totally 6 experiments for 10 center points. So this comes to 46 experiments. So you need to do 46 experiments if you want to do the Box-Benken type of design. Okay, now let us do the CCD, which is called the Box-Wilson design. Okay, the CCD is called the Box-Wilson design. In CCD, what do? You do the factorial, and then we do the center points, and then we do the star points, or we call it alpha points, they call it alpha points. So, if you are doing the factorial could be a 2 power 3 or it could be a 2 power 3 minus 1. Okay, let us look at the full factorial. So, we have the 8 experiments for the factorial. This is the first 8 experiments of the factorial. So, we have all the combinations for ABC, that is 8, and then we do, okay, these are the center points. So, we will be doing 6 experiments for the center points. I will tell you why you need to do 6 experiments, and then we do the star points or the alpha points, that means A at plus alpha and minus alpha, B at plus alpha minus alpha, C at plus alpha minus alpha, that comes to 20 experiments. Okay. Why do you need to do 6 at the center point? There is a formula which is like this: NC, that is number of center points, is equal to 4 square root of NF plus 1 minus 2n, where NF is the number of factorial experiments. So, in this particular case we are doing 8 experiments, that is 2 power 3 full factorial. So, that comes to 8 plus 1 9, square root of 9 is 3. So, 12 minus 2n is the number of factors, okay, number of variables or factors that, okay. So, here we have 12 and here we have 2 into 3 6. So, 12 minus 3 6 is 6. So, we are doing 6 experiments. We can do the same Box-Wilson, but instead of factorial we can do a fractional factorial, that means 2 3 minus 1, that means we are doing only 4 experiments for the factorial region, and then the remaining is the center points, and then plus alpha minus alpha plus alpha minus alpha plus alpha minus alpha. Here we are doing only 3 center points, because according to this formula 4 square root of NF here is 4. So, 4 plus 1 is 5, square root of 5 is 2.236 multiply by 4, so that is about 10, and then minus the number of n is 3 here. So, you will end up with 3 center point. Okay. So, depending upon the number of runs you are doing in the factorial, the formula is given where you substitute that. So, if it is a 2 power 3 full factorial, we will put NF as 8. If it is a 2 power 3 minus 1 fractional factorial, we will put NF as 4. That will give you an idea about the center points. Okay. So, this is how you build up the Box-Wilson CCD. Okay. Okay. So, we have looked at different types of 3 level designs, which are also called non-linear designs. So, we have the 3k minus q, this is exactly like your 2n minus q type of thing. Okay. It can be used for qualitative or quantitative factors, we can use it for linear and quadratic effects. Okay. You can also estimate linear and quadratic interactions, that means I can put a square or a into b type of terms in my regression. Okay. Okay. So, this can be done actually. Now, we looked at Box-Benken design. So, we can use it for quantitative factors. Okay. Of course, we can also use it for linear, quadratic, two-way linear interactions and so on. Then we came to CCD. Okay. The advantage of CCD is it can look at almost 5 different levels, because we are having star plus alpha plus and alpha minus, unlike any other designs we are talking about. Okay. We can estimate linear effects, quadratic effects, two-way linear interactions and so on. Then the full factorial 3 raised to the power k. Okay. So, we are going to have large number of experiments here. We can use it for qualitative or quantitative, we can use it for linear, quadratic effects, also all types of interactions, two level interactions, 3-way interactions and so on actually. This is a full factorial design. Okay. So, this is a comparative table, full factorial. If I am having k is equal to 3, that means 3 factors or 3 variables, 3 raised to the power 3, 3 into 3 into 3 is 27, and then if it is 4, sorry, 3 into 3 into 3 into 3 81. So, it grows up exponentially. If you come to CCD, if you assume a fractional factorial for the central portion, and then we consider the center points as well as the star points, you will have 13 experiments. If you remember this, okay, if you remember this, we have 13 experiments, right. So, we can have 13, whereas Box-Benken will give you 15 experiments. If you have 4 variables, then we can have a 27 experiment, that is we can build up a 1/3 factorial type of design. Box Benz gives you 27, this tells you how many center points, and CCD fractional factorial for the central portion will give you 20 experiments, and there will be 4 center points, like that, you know. So, as you can see, CCD appears to be very efficient, okay, when compared to any of these design, box Benz or 3k minus q or full factorial design actually, okay. And also you can see we can get center points, that is very important. Both these designs give enough number of center points which will help you to estimate the errors, okay. So, CCD appears to be the best if you are looking at a quadratic type of model or higher order models. So, we looked at a large number of design strategies, we looked at the screening design strategy, then we looked at the second order design strategy. Here we have the box Benz, we have the central composite designs, we have the of course the full factorial 3 level designs, then we have the fractional factorial 3k minus q type of design, and so on. So, once we have these designs, what do? We can perform an ANOVA, okay. Once we perform an ANOVA, we will know which factors are important, we can look at whether any interactions are important, then we can go into regression, we can develop regression relationships, okay, and then get a model. If it is a second order model, that means if it is a quadratic model, we can optimize that model. By doing an optimization, we can find out the best set of parameters at which say my yield is maximum. Then I can go and test it out in my actual reactor, bioreactor, or whatever system I am looking at, to see whether I got the same answer as predicted. So, ultimately you want to optimize or maximize your productivity, maximize the yield of the metabolite, maximize the yield of biomass. So, obviously once you perform your design calculation, you shortlist the best set of parameters, you identify which parameters are going to play an important role or significant, eliminate the other parameters, then you develop a regression relationship, and with the regression relationship you optimize your product yield. That means you change the parameter values theoretically, using the regression relationship you change the parameter value and find out the best set of parameter values which give you the maximum yield, and then you can go and test it out in your lab, and you can say this is the best type of conditions at which I should operate my bioreactor. So, this is how the sequence of events take place when you talk looking at the experimental design strategy. Okay, so that means I need to have a good knowledge about my regression, what type of regressions to use and what type of models I need to use, and so on actually. Okay. So, let us look at some of those regression approaches by which one goes about doing the modeling. Okay. So, what is regression analysis? Okay. So, regression methods are used to develop simple empirical models. So, we can get y is equal to a plus b x1 plus c x2, where x1 x2 are my parameters. If I have a second order model, I can use it for a equal to b x1 plus c x1 square plus d x1 x2 and so on. We can get some actual understanding of the physical phenomena, we can correlate design variables. Okay. So, we can do so many things with the regression models, and the typical regression methods use a simple regression method, multiple regression method, multiple linear models, partial models, backward regression, and non-linear models, second order models, or and so on actually. So, regression we can do so many things with the regression models. Okay. So, regression can help us to understand which factors are important. Of course, we can do it through ANOVA also, as I have been talking about it in the past so many classes. Okay, so, it can, of course, the regression also tells you depending upon the parameter which you get which ones are good. We can use it for predictive. Like I said, I can optimize the conditions and then I can say if I operate at this temperature, this pH, this carbon amount, I will get maximum yield. How do I do that? I can take the regression model, I can modify the conditions and see whether I am able to increase the productivity. That is called simulation, and that is called prediction. So, you come up with the new operating points. We can use it for estimating the coefficients. What will be the constant that gets multiplied with temperature? What is the constant that gets multiplied with the pH? The constants also tell you something very important. It tells you what is the effect of each of these, what is the quantum of effect or the weightage of each of these parameters on my total yield, for example, if that is what is my desired. Okay. So, regression has lot of uses. It not only developing an equation, it can be used for later optimization, simulation, model predictions, new scenario generation, looking at which factors are important, which factors are not important, whether some factors are positively correlated, whether some factors are negatively correlated, and so on actually. So, regression analysis is extremely important if one wants to do a proper analysis. Okay. So, what are the approaches? We pick a regression model. So, do I go for a linear regression model? Do I go for a non-linear regression model? Do you have x1 square? Do I have x1 into x2? That is interactions. X1 square means it is a quadratic, x1 in x2 means it is an interaction. So, I need to decide, do I go for a linear model, non-linear model? Then you gather the data, of course, you collect enough data, you know which parameters are important after performing a screening design, then you perform the regression analysis. That means you actually fit your data to the model you have selected and then estimate those constants A, B, C, whatever it is, okay, the constants of this regression model. So, you need to decide on which model to consider, that is very important. So, a priori you say I will take a linear multilinear model, that means A plus Bx1 plus Cx2 plus Dx3 like that, that is a multilinear model. Or I will say I will take a single parameter quadratic model A plus Bx1 plus Cx1 square, or I will take a 2 parameter model with quadratic terms, that means A plus B x1 plus Cx2 plus D x1 x2 and E x1 square plus F x2 square, like that, you know. So, you need to a priori decide, but later on when you do the regression analysis, depending upon your A, B, C, D, you may neglect some of the parameters, okay. If the parameter values are very small, you may do that, but you need to anyway consider a priori what type of model you will do, okay. That is very important, okay. Then you perform the regression analysis and you select the best model for your based on the R square, based on the ANOVA. So, like that finally you end up with the best regression model for your system. So, regression is nothing but a curve fitting for a single parameter. That means if I am measuring flow as a I am measuring pressure as a function of flow, flow is your independent variable, your pressure is your dependent variable. So, if it is a linear model, I will have y equal to A plus that is pressure is equal to A plus B into flow. If it is a second order model, I may say pressure is equal to A plus B flow plus C flow square. So, when I fit the data, I can estimate A, B, C, okay. So, in this particular case I may think it is not a linear, it is a non-linear. So, I will take A plus B flow plus C flow square. For a 2 parameter, of course, suppose I have x here, y here, z is my dependent variable. So, I will have a linear model will be y is equal to a plus bx1 plus cx2, a non-linear model will be y is equal to a plus bx1 plus cx1 square plus dx2 plus zx2 square plus fx1 x2 also, if you think there is an interaction, okay, and so on actually. Then you estimate the constants a, b, c, d, e, f. By fitting the data you determine the error. What is error? What is predicted by the model minus what is actual, square it up, sum it up, that is the error sum of squares. So, from there you perform an ANOVA and then you see whether the model is really predicting the data or not, okay. So, that is quite straightforward and that is what you do in your regression analysis. So, basically it is a curve fitting for a single parameter, curve fitting. So, it is easy in a one dimensional system, that means single parameter, or even a 2 dimensional system to visualize, but if it becomes higher dimension we cannot really visualize, we have to look at the error sum of squares and then make a conclusion whether the error sum of squares is very large for one model, I have another model, I get another error sum of squares, I can compare both of them and say yes they are very different or no they are not very different. But if I am having a very simple single parameter or a 2 parameter model, I can even visually plot them and I can say yes this model looks good, okay. But for larger systems it becomes more difficult, you will not be able to tell unless you actually calculate the error sum of squares, okay. So, that is very important and we will go down as we go along to and I will tell you how to calculate these various parameters and how to estimate the constants of regression, the multiplication factor or the slope of regression line and so on. And Excel also has that option to determine both the slope as well as the intercept for the regression line, okay. So, if we can visualize the data, there are different relationships that are possible. Suppose I take a parameter x here, that is the independent variable, and this is my dependent variable y, okay. I can have different types of relationship, that means y and x are highly correlated, okay. As you can see, as x increases y also increases, whereas here if you see this data, as x increases y is all over the place. So, this is a 0 correlation, this is the best correlation. So, in between you can have different numbers possible, okay. In between you can have different numbers possible and different figures. Look at these figures, not at all correlated, little correlated, highly correlated. So, you can have correlation coefficient varying between 0 to 1 and if it is 1 as x increases y also increases, if it is minus 1 as x increases y decreases. So, you can have both the situations, the direct correlation or indirectly related or positively related, negatively related, and this is called the correlation coefficient, and I will tell you how to estimate the correlation coefficient also. But it becomes very easy if you have one parameter. To calculate the correlation coefficient, okay, there is something called a covariance. Covariance tells you the strength of the correlation between 2 or more sets of random variables x and y. So, how do you calculate? It is given by this formula, covariance x y summation of i's varying from 1 to n, xi minus x bar is the average of all the x's, yi minus y bar is average of all these y's divided by n minus 1. This is called the covariance. It tells you the strength of the correlation, and the correlation coefficient is given by covariance of x y divided by sigma x sigma y. Sigma x is, what is sigma x? Xi minus x bar square divided by n minus 1. What is sigma y square? Y minus y bar square divided by n minus 1 summation. Okay. So, correlation is a scaled version of covariance. You are scaling it down with respect to the sigma, that is standard deviation x and standard deviation y. Okay. So, as I said, once you collect the data, we need to perform a regression analysis, and before the regression analysis we actually look at the correlation coefficient between x and the y, that means the independent variable and the dependent variable. So, if I have many x's, that means I have temperature, pH, carbon amount, okay, and for each one of them I have the yield data. So, I can perform a correlation analysis, I can calculate the correlation coefficient between temperature and the yield, between pH and the yield, between carbon amount and yield, to see whether my correlation coefficient value is very high or very low, whether they are correlated or not correlated. Okay. So, you can do that as your first step to analyze your data. Okay. So, we will continue on this regression analysis in the next class also. Thank you very much.